So today let us see alkanes preparatory methods. So alkanes are saturated compounds. They don't have any unsaturation in them. They are also called as paraffins. So this is the first topic under hydrocarbons. So let's see the preparatory methods of alkenes today. So alkenes can majorly be prepared from three rough categories. So the first category is from alkyl halides. So alkyl halides means RX. So there are four different reactions you can do to alkyl halides so that you get alkenes. The second category is from carbonyl compounds. Any compound containing C double bond O in them are called carbonyl compounds. So you have two reactions under carbonyl compounds, Clemenson's reaction and Wolff-Kishner reaction. So with these reactions, you can get alkenes. So there are some other reactions also like hydrogenation, cold electrolysis, decarboxylation, and Grignard reagent. So let us see all the preparatory methods today. So first preparatory method today is reduction of alkyl halide. So now I take RX, that is alkyl halide. I introduce some reducing agent. So this reducing agent would form RH. RH will be alkane. So what is the role of this reagent? Role of reagent is to produce nascent hydrogen. Means this reducing agent which we are adding here, the reagent, it is helping in production of nascent hydrogen. So nascent hydrogen helps in breaking of bond and attaching of H. So what are the reducing agents you are using in reduction method? So we have many questions in alkenes. So reagents are very important. So we have Zn zinc with zinc with HCl or zinc with NaOH. So when you take any bivalent method, you can clearly understand that you are reducing it. Zinc, you can clearly understand you will reduce it. So zinc copper couple with ethanol, C2H5OH. These all reagents are important. All reagents are important. So we have LiAlH4 and ether. Okay. And then we have right, NaBH4 with ethanol. I'll write ethanol. Okay. So we have um, right, PH3 SNH. Okay. PH3 SNH. So it is triphenyl tinhydride. It is also called as TTH. Okay. And the most important of all is red phosphorus. Red phosphorus with heat. Okay. So red phosphorus with HI. Okay. This is the most powerful reducing agent in whole organic chemistry. So what are the reagents? Zn plus Zn with HCl or Zn with NaOH. So we have zinc copper couple with ethanol, or we have LiLH4 with ether, or NaBH4 with ethanol. We have TTH, okay, which is a triphenyl tinhydride, and then we have red phosphorus with HI. So this is reduction of alkyl halides. So with this reduction of alkyl halides, you can easily get alkene. Now, the second preparatory method here is Wood's reaction. So Wood's reaction is a famous preparatory method of alkenes. So important point under Wood's reaction, it gives good yield per carbon containing, or the chain containing even number of carbons. It is an important point. Many questions are asked on this. Carbon containing, the chain containing even number of carbons. So let's see the first one. Means how Wood's reaction takes place. So you take an alkyl halide. Here all will be regarding alkyl halide only. So you take alkyl halide and then you add Na, 2 moles of Na, and then you the reaction takes place in the presence of dry ether. Okay, dry ether. And then what would form is RR, or if you take R dash X, uh, right? So, or you can add R dash X, or you take 2 moles of Rx. So you can get RR or RR dash. Okay, these two will be your products, and then a minimum amount of R dash. Okay, plus 2 NaX. So this is Wood's reaction. Means you are taking alkyl halide. You can take 2 moles of alkyl halide, or you can take two different alkyl halides and you add it with Na dry ether. And then you are getting alkanes. And 2NaX is the byproduct. So let's see mechanism. So mechanism, let's analyze the mechanism using an example. Okay, so let me take CH3CH2Br. Okay, so I am taking CH3CH2Br, which is an alkyl halide. So when I take 2 moles of it, okay, so first of all, homolytic cleavage takes place. There will be a free radical with the alkyl chain, a free radical with a free electron with bromine. So what would happen next? We have Na, right? We have added Na, 2 moles of Na. So this 2 moles of Na will react with these two Br, and then these two Br, and 2 moles of NaBr is formed. Okay, and then we have two radicals now. CH3, CH2 radical, and then CH3, CH2 radical. Now you have to add these radicals. So one way you directly add them. So butane is formed here in butane, which will be the major product here. So disproportionation can take place, and then this kind of product is also formed, C2H6 plus C2H4. Okay, disproportionation can also take place, and lesser alkanes can also be produced. So this is the mechanism of Wood's reaction. It gives good yield in case of carbon containing even number of carbon, the carbon chain containing even number of carbons. Okay, so this is Wood's reaction. So let's do some example on Wood's reaction. So let me take butane and then 2 moles of Na in presence of dry ether. So what would happen? So first of all, so okay, you need an X here. Okay. Now, what would happen? Just homolytic cleavage takes place, and then you take 2 moles of it, and then you have another one. Okay, just join them, then you are done. So you have another bond like this, right? Another bond like this, another, it's connected. Okay, so you have 4 carbons here, you have 4 carbons here. You should have eight carbons here, right? 1, 2, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Right. See, so this is how you do the Woods reaction. Another question of Woods reaction can be something like this. So we have a bromine here, we have a bromine here, two bromines. So let's repeat 2Na plus dry ether in presence of dry ether. So what would happen? Here you can see a radical is formed. Here also a radical is formed. So this will be the product formed. So these questions are based on Wood's reaction. Now we have seen Wood's reaction. So let's see Franklin reaction. So Franklin reaction is a reaction where we take alkyl halide. Okay. So we are going to use alkyl halide here also. Okay. And then here the reagent is important. So you are adding zinc. Okay. In presence of ether. In presence of ether. Zinc in presence of ether. So what would happen? R would be formed. Mechanism is not of that importance, but you can just have an idea that here RH is not formed, R is formed. So this is important here. Okay, so this reaction is called Franklin reaction, where you add zinc in presence of ether, so RR would be formed. And the byproduct is ZnX2. Now, the fourth reaction is Corey-House synthesis. Okay, so let's see Corey-House synthesis. Corey-House synthesis. So let me just give you a structure so that you can remember the process well. So the main thing of Corey-House synthesis is you take an alkyl halide. Okay, you take an alkyl halide. You first react it with lithium. Okay, 2 moles of lithium to be precise. So when you react it with 2 moles of lithium in presence of ether, okay, what would be formed? RLi is formed, means alkyl lithium, and then lithium alkyl. So, and again LiX will also be formed. Now, you take this alkyl lithium alkyl, lithium alkyl, and then you treat it with copper iodide. This is important here. Lithium ether, and then you are going to react it with copper iodide, and then what would be formed? R2Cu Li. R2Cu Li is formed with sorry, lithium iodide. Lithium iodide is formed. Okay, so this is an organometallic compound again. So you react it with you react it with another alkyl halide. Now let's call it R dash X. So what would happen? R and R dash will make a bond. This is an important step. R and R dash will make a bond, and then the byproduct will be RCU plus LiX. So these are the byproducts. So step one will be lithium plus ether. Okay. Step two will be treating with copper iodide. And step three is adding another alkyl halide. Or it reacts with itself. Okay. So another RX can also be formed and R bond R can also be formed. So this whole process is called Corey-House synthesis. Mechanism is not of that importance, but yeah, you have to just remember the three steps. Now, we are done with from alkyl halides. We have seen all reactions. Now let's see from carbonyl. From carbonyl compounds, we have two reactions: Clemenson's reaction and Wolff-Fishner reaction. So Both are the same reactions except the reagent is different. Okay, so first let us see Clemenson's reaction. Clemenson's reaction or Clemenson's reduction, whatever you want to call it. So in Clemenson's reduction, what do you do is you take a carbonyl compound, C double bond O, and then you react it with the Clemenson's reagent, which is a very important reagent, which is ZnHg. ZnHg in presence of HCl. Okay, ZnHg in presence of HCl. So this is called Clemenson's reagent. So what would happen? Just replace the double bond O with two hydrogens. Yeah, sorry. Okay, so you have R prime. Here also you have R prime. Just replace the double bond with two hydrogens. So this is Clemenson's reaction. Again, the mechanism is not important. You have to just remember that remove the double bond and put two hydrogens. So after Clemenson's reaction, we have Wolff-Kishner reaction, a very famous reaction. Wolff-Kishner reaction or reduction. So you take the carbonyl compound and here you will use Wolff-Kishner reagent. What is Wolff-Kishner reagent? It is hydrazine in presence of C2H5O minus and Na plus in this medium, or you can do it another way like this. Here we'll use hydrazine. Okay. Here also we'll use hydrazine, but we are adding KOH and then ethylene glycol in presence of ethylene glycol. Okay. In both cases, you can break the product CH2 R prime, CH2 R prime. This is called Wolff-Kishner reagent. So when you add the carbonyl compound with the Wolff-Kishner reagent, you are going to get a alkane, a straight chain. Here also we have seen Clemenson's reaction also. Here we will use Clemenson's reagent, which is ZnHg in presence of HCl. So you can use hydrazine. What is hydrazine? Important, right? So hydrazine, which is NH2, NH2, N2H4. Wherever you see N2H4 or NH2, NH2, it represents hydrazine. Okay, so this is Wolff-Kishner reaction. And with this, we have completed both from carbonyl compounds. So we have some other reactions. So let's see hydrogenation or catalytic hydrogenation. Hydrogenation is a famous method of preparation of alkenes from unsaturated compounds. Okay, so you take alkene or alkyne or alkyne. Okay, we took alkene or alkyne. So here important, you are adding H2. Okay, let me explain alkene first and then let's go to alkene. So we are going to use the hydrogenation catalyst. So this is a catalyst here, hydrogenation catalyst. So it is nickel, palladium or platinum. Nickel, palladium or platinum at temperatures of 200 degrees centigrade to 300 degrees centigrade. Okay, so at 200 degrees centigrade to 300 degrees centigrade. Okay, so with this catalyst, very important catalyst, 200 degrees centigrade, even temperature is important here. The pi bond would break and then this hydrogen will go and attack here. Okay, so what would form? C, just a hydrogen. This is called catalytic hydrogenation. Now, in case of alkyne, there are two pi bonds. In order to break two pi bonds, you'll need 2H2. Okay, 2 moles of H2. So when you add 2 moles of H2 or excess of H2, what would happen? with the same catalyst, alkane is formed. Okay, so this is called hydrogenation. That's it. This is also called as Sabatier-Senderens reaction. You can just see it in any book. Okay, so this is hydrogenation. Now, after hydrogenation, what do we have? So after hydrogenation, we have Cole's electrolysis. Okay, so we have 10 reactions in total. So let's see Cole's electrolysis. Cole's electrolysis is also very famous preparation of alkane. So as the name suggests, you are going to electrolyze something here. Electrolysis means electro means electricity, lysis means breaking. So breaking in presence of electricity, it is called electrolysis. So what is Cole's electrolysis? Now, you take carboxylic salt of some alkane, COONA. Okay? When I take carboxylic salt of Na, 2 moles, or if I take two different salts also, I have no problem. But better yield will be of 2 moles, as we have seen in many reactions before. So we are going to electrolysis with 2H2O, electrolysis, 2H2O, electrolysis. What would happen is R and R dash, as you have expected. You can just guess the product. R and R dash will form the product, and then the side products are 2CO2, okay, and then you have H2, and then NaOH. These three are the byproducts, which are of least importance, but R and RH is the product we need. So how does this happen? So let's see mechanism of Cole's electrolysis. So let me take a suitable example here. So CH3, COONA. I'm taking 2 moles of CH3, COONA. Okay. Now, what do I do is, yeah, now this COONA, whatever you can see here, right? COONA, COONA. You want it to be eliminated. So how can it be eliminated? So we have CH3, Na plus is released. Okay, Na plus is released. So what do you get? COO minus CH3, COO minus. CH3, COO minus. What would this next happen is, this will give out electrons. Okay, these are two extra electrons, right? Two extra electrons. So what we will do? CH3, COO radical plus 2 electrons. Okay, and just writing like this. So 2 moles of this, each will give 1 radical and then 2 electrons. So 2 CH3 COO minus are going to turn out 2 electrons. So these 2 electrons, so this reaction happens at anode. Okay, here whatever we are discussing happens at anode. So we are dealing with the negative charge, so it happens at anode. Now, CH3CO minus 2CH3, a radical is formed and 2 electrons are formed. Okay. Now, what would happen? You can see here the structure of carboxylic acid, CO. So it has 1, 2, 3, 4, 5, 6. Okay. One extra electron. That's right. One extra electron, which it got through radical. Now, this bond will shift here. Okay, this bond will shift here and it will form C double bond O. C double bond O. What is this? It is nothing but, as you expected, CO2, carbon dioxide. Okay, so carbon dioxide is released and the remaining radical. So here we can clearly see homolytic cleavage is taking place, right? So you'll get two CH3 radicals. Okay, so we will get two radicals of CH3. So what would happen next? CH3 bond makes a bond with another CH3 and CH3 a bond is seen. So this is how the anode reaction takes place. At cathode, what happens is these two electrons are there, right? These two electrons are accepted by H2O. So we have H2O, it accepts electrons and it turns out to be OH minus and H radical. And again, because of constant production of these H radicals, so two H radicals would combine to form H2 gas. Okay, these are the cathode reactions, these are the anode reactions. This is complete Coles electrolysis. The important point here is you're going to electrolyze it and R dash bond is formed. A new carbon bond is formed. Okay, so this is Coles electrolysis. And the next reaction is from Grignard's reagent. Okay, cool. So we have Grignard's reagent. Grignard's reagent is a famous reagent used in many organic reactions. So it is RMGX. Okay, RMGX. It is an organometallic compound. So here this is an ionic bond. Okay, so you get R minus MgX plus. Okay, now how do you prepare Grignard's reagent? It is pretty simple. Take alkyl halide. Take alkyl halide. React it with Mg dry ether. So when you react Mg dry ether with alkyl halide, RMGX is formed. Okay, this is the preparatory method of Grignard's reagent. Not that important, but this is just information so that you can know. Very simple, alkyl halide, add Mg in presence of dry ether, RMGX is C. So here you can clearly see R minus is there. Means on carbon, there is negative charge. On carbon, when there is negative charge, it can act as base. And it can, of course, act as nucleophile. Okay. So when it is acting as base, what is the point? In order to neutralize it, you need acid. Okay. So you got your answer. So here R minus is releasing in the solution. Now, when R minus is releasing in the solution, we are going to add an acidic hydrogen to it and RH bond is formed. So let's see the reaction now. So we'll take Grignard's reagent, RMGX, and then let's add any compound which will give H plus. So that is called active hydrogen or acidic hydrogen. So when acidic hydrogen comes out, what would it form? RH bond is formed, and then a covalent bond, sorry, an ionic bond is formed here between MgX, okay, between MgX and the other, this thing, the other thing. Like, let me explain. Now, let's take H2O. This hydrogen is released. This hydrogen will go and react with the R minus that is produced. So RH is formed. And we have OH minus left over here. So there will be an ionic bond between MgX plus and OH minus. Okay. So similarly, let's take another example. Let's take HX, acid. So R minus. This hydrogen will go attack this. RH bond is formed. And then this thing is formed. MgX and then an ionic bond. Okay. So this is how you write the byproduct in case of this thing. And the main important thing you have to remember is the active hydrogen goes and reacts with R minus. So it, because it acts as base. Now, this is from Grignard's reagent. Let's see the last reaction of today. That is decarboxylation. As the name suggests, decarboxylation. So removal of CO2. Removal of CO2 is called decarboxylation. So in decarboxylation, mechanism is not really that important, but the very, very important thing is reagent. Okay, let's see. We will take sodium salt of carboxylic acid. We'll take sodium salt of carboxylic acid, okay, and then react it with a reagent. So R CONA, right? This is the sodium salt we are taking today. So when you are going to heat it with soda lime, or I'll write like this, CaO plus NaOH. Okay, this is very, very important. Many questions are there on this. So let me highlight this, do whatever, right? This is a pretty important thing. It is called, oh, sorry. This is called soda lime. So when soda lime is reacting with the sodium salt, what would form? RH. And then the byproduct will be Na2CO3. The mechanism is not important, but the reagent is very important. So when you are going to take sodium salt of carboxylic acid and react with soda lime, so RH is formed and Na2CO3 is formed. So this is called decarboxylation. Means it is formed by removal of CO2 in the mixture. So that's it. These are the preparations of alkenes, right? And then here, once revising everything, hydrogenation we have seen, where you add H2 in this catalyst, RR is formed. So let's see Kolbe's electrolysis, where you are going to electrolyze using H2O, CO2 is formed, RR bond is formed. Decarboxylation, soda lime is the important thing, RH bond is formed. Grignard reagent, you want active hydrogen. So from alkyl halides, we have four reactions: Wood's reaction, reduction reactions, Corey-House synthesis, and then Franklin. So what is Wood's reaction? Na plus dry ether is a reagent, and a new carbon-carbon bond is formed. In Franklin reaction also, new carbon-carbon bond is formed. That's why RR is formed. In Corey-House synthesis, you use Li and ether, and then you treat it with cuprous iodide, and then add another alkyl halide. So you'll get RR. And from carbonyl compounds, and we have seen reduction reactions. These are the various reduction reagents. The next one is carbonyl compounds. We have Clemenson's reaction. We have Wolff-Kishner reaction. In Clemenson's reaction, the Clemenson's reagent is used, which is ZnHg in presence of HCl, and Wolff-Kishner reaction, we have hydrazine in presence of C2H5O minus and Na plus. So that's it. This is preparatory methods of alkenes. Thank you.